This is a repeat of the talk that I did last year with a few minor updates, which I'll probably comment on. So this is me, Jørgen. I run Patch. I'm for hire. The last year, well, 2 years, I suppose, I've been implementing the support for the prime path coverage in GCC. So this talk would outline what that is, what that means, and roughly how you use it. Lovely. I've detailed the implementation in a paper with all of the algorithms and everything, which you can get from there. Give it a second to maybe get the link. Otherwise, obviously, just search for it, ask. If you search the terms prime path coverage in GCC, the paper usually shows up in the search engines. So I think prime path coverage is the next step in structural coverage. And I will actually go so far as to say as is the next generation of structural coverage. So let's do a wee bit of a history there. This is a new feature that landed in GCC 15. We made the release if you were here for last year. Yay! So in 1997, I had to go back in the GCC Git log to figure this out. But the first coverages came in GCC 3.4 in 1997. And it was actually kind of a side effect of the profile-guided optimization support. In 2024, I added MCDC to GCC. And then now in 2025, we have the prime path coverage. So this hasn't been a very fast-moving field. But we made a leap. It turns out in 2023-24, Clang also did MCDC support. And also hadn't had anything before that. So everything happened the same year after 1997. It was funded by NASA, driven by their needs for spacecraft software. And this is how they test their flight computer software today. That actually makes me very happy, because when the people return to the moon, I will get to watch the landing and think that I was a small part of that. So that's very cool. OK, so let's start with structural coverage and summarize where we're at. So you're probably familiar with the first one there, which is statement or line coverage. Statement coverage, I think, is a better metric, but hardly anyone ever do it. And pretty much a statement is anything up to the semicolon, right? So that one you're familiar with. Did you visit this line or not, right? So branch coverage is sometimes called decision coverage, depending on where you're from. And that's really trying to figure out, did you take both the then and the else case in every condition in your program? Condition coverage is where you need to check that you're doing both the true and false outcome of every term in your condition. So if you have a multi-term condition or decision that you need to make, so you have A and B and C, you want to show that all of them have taken on both true and false. MCDC adds the additional constraint that you need to show that each of these terms have the power to independently affect the outcome. So we'll look a little bit more at that later. So yeah, statement coverage, every statement has been executed, decision, every decision has been made. When we say true, false, that roughly translates to the then else when you're putting it in an if, right? But this actually applies to if you would assign a complex Boolean function to a variable, you still need to measure this, right? You can't hide it by folding it. Yeah, so condition coverage, every condition has taken on both true and false. So in this case, in order to test that, you need to run it with true, true, true in order for the C to become true. You need to run it with true, true, false to show that the C can be false. You need true and false to see that the B has been false, but it's already been shown to be true. And finally, just false, which short circuits the rest. MCDC has this additional constraint. This is called the independence criterion, usually. You need to show that every condition has taken both the true and the false while having independent decisive power. Now, what that means is that assuming you fix the rest of the inputs, like in this case, we fix the true and true for A and B. If we were now to change the value of C, you should see that the outcome changes, right? And in this case, it does, which shows that the C taken on false has the power to independently change the outcome. This is what we're trying to prove. What all of these metrics so far have in common is that they're really concerned with single lines or statements or expressions, so they're pretty local. They're limited in scope, and they focus on the individual sort of units of your program. So you have a line of code, that's the unit that you're testing, right? So you're doing individual statements, you're doing individual decisions, and you're doing the individual conditions of the individual decisions. So it's starting to, have a little bit more, a larger window that we care about. But really, what we care about is data flow sometimes. And data flow is really the analysis. I think this is the definition if you look it up. It's the analysis on the data dependence between when variables are assigned and written and used. So data dependence is about the questions. A variable is used here, and then the questions are, where does it come from? Is it ever used? Is it initialized? And what is affected if you write by it? Compilers do this kind of analysis all the time. For example, to figure out, hey, you're not actually reading this after writing it. I'm just going to omit the write. Like, why do you care? Can't observe the difference. Now, MCDC is fundamentally really a data flow problem that is masking as a structural one. There is an even beefier kind of coverage that pretty much nobody knows about, which is called definition use pairs. And it is the associations of the definition and uses capture the flow of information throughout the program. This is one of the things that you can read and you're like, what happened here? I have no idea what this means. I still have no idea. So in this definition, definitions occur when variables are declared or initialized, assigned, or received as parameters. So they're parameters to functions. In the definition use coverage, this is what the definition bit of it is. And then the use is when it shows up in an expression, in a conditional statement, in a return statement, or passed into another function as a parameter. That's considered a use. And what we're concerned about here is exercising every pair of decision use of every variable in the program. This is a binary search that I stole from the internet. That I think someone wrote in Python, and I ported it to a sort of C-like thing. Actually, a Python-like thing, but I removed the colons. And I've annotated this where the definition use pairs. So on the first line there, you define the min. On the second, you define the max. And then you use the min. The n and min is now the same thing. Sorry, there's a typo there. On the third line, you define the mid, but you use the max and min to compute it. And so on, right? Right mess. So to achieve definition use pair coverage, you need to ensure that every pair of these definition uses have been exercised or executed. Now, the big departure here is that the definition use detect longer range effects, right? So for example, here the mid is defined on line 3, used in 4, then it's redefined in 5 and used either in, 8 and 10 maybe. So in the then and else case of the condition inside the loop. So if you were to only do the then cases, you would never exercise the definition use pair where the mid is in the else. Okay? So we're able to see relationships and effects at a longer distance than beyond a single statement or expression. So this is an example that John Reger posted on his blog years ago, So it's quite possible, and he did this to illustrate how poor coverage sometimes can be in order to find defects. Like, it can be quite expensive to achieve coverage, and it can still be hilariously bad at detecting problems. So in this case, it's very easy to have full branch or line, branch, condition, decision, and modified condition decision coverage, and still miss the case where you dereference the null pointer. This is obviously silly because it's 3 lines, right? But imagine it looked like this. And this was actually the effect that something on the 3rd line happened inside a function call that you didn't really see, right? This happens. Now, the definition used would detect this, because the P could be defined on line 3, and you would have to match it to the pair at line 120. So let's do a detour into graphs and basic blocks. We represent the structure of programs as graphs. And this is what happens inside the compiler. The compiler will construct a graph that corresponds to your program, to do a bunch of analysis and ideally optimization on it. It's a very powerful abstraction for the structural analysis. So let's start with the definitions that we're working with. So a basic block is an uninterruptible stream of instructions. Okay, so once you enter a basic block, there might be multiple ways out, but you will always reach the end, and you will execute every statement in there in order. The edges of this graph are the transfer of control between the basic blocks. So this is the same program that we had before, but rendered as a graph. And this is roughly the structure that the compiler works with internally. So the first basic block, there's no divergence there, right? So it defines the min and the max, and it computes the mid. And from there, it jumps to comparing the mid to the element that we're searching for, the needle. Depending on the outcome of that comparison, we either return, or we go into the loop, we continue evaluating whether or not we've exhausted the range that we're searching before doing the loop thing. Like, this is a binary search, you know how it works. Now, this structure was not at all that obvious when you were looking at it in source code, right? But now the structure sort of leaps out at you. And you have some interesting things too that happen. So for example, the lower pair of blocks there where you assign to either the min or the max, these were serialized in code, but now they're side by side. So it's kind of clear that you're going either way, but you're not doing. Keep cutting. Sorry. Okay, so usually then we just simplify it and we number these, because the code can get quite unwieldy, and we care only about the structure of the graph here. Now, prime path coverage works at the function level, right? So the paths are associated to the function and not to specific lines. So let's take this program, which is just a sequence of an if-else, right? Straightforward. If you look at this as a graph, and we remove the actual code of the then else and we just replace them with numbers, it will look something like this, right? Okay. We have 4 paths through this function. We can exercise let's say that the path or the edge to the left there, so 2 to 3, that's the true, and the other way is the false. So we need to do the true and then true. Sorry, true and then false. No, hang on. True and true, true and false, false and true, and false, in order to exercise all the paths. And these are the possible paths of execution through this program. Depending on the input, you do 1 out of 4 computations. By definition, a walk is a sequence of edges which joins a sequence of vertices. And a path is a sequence of edges which joins a sequence of vertices in which all the vertices are distinct. Paths provides us with 2 problems. You have loops, and you have the path explosion problem. So a problem with most path definitions And loops is that doing the loop once and doing the loop twice might be considered different paths. So n iterations will be different from n plus 1. Now, obviously, this doesn't work. It goes to infinity, right? You can take the loop very many times. Even if you bounded this would be very impractical. And what would that boundary be, right? So loops have been a problem in coverage and analysis for a very long time. So in the 1970s, the goal was just to execute the loop once. Like if you can go through it, we're fine. Later in the 80s, the focus was on figuring out how to measure, or if we did loops exactly once. We wanted to do that as well. This is sort of additive. In the 1990s, the goal was to exercise all the paths that would execute loops more than once. And now in the 2000s, we're able to deal with prime paths where you get phenomena like touring and side trip and detours. We're not going to go into those too much, but they all together compose the prime paths. Then there's the path explosion problem. So even quite small graphs with maybe a dozen, 2 dozen blocks may have a large number of paths. Now, a simple path is a path where all the vertices are distinct. And a simple cycle is where only the first and the last vertices are equal. Now, the prime paths, or the prime path coverage goal is to take every simple path and simple cycle in the program. So going back to the sequence of if then else, we have 41 simple paths and cycles. So we want to exercise all of these 41. Okay. Miserable, right? This is a graph with 2 if then else, and we have 41 things that we need to measure. No. Because these 4, if you could do these 4, they would actually cover all of the other ones, because all of the other paths in this picture are contained in either of these 4. They're a part of either of these 4, which is where the prime thing comes in. So a prime path is a maximal simple path or cycle, right? The implication here is that loops, they must be taken, skipped, and exited. Which sounds reasonable. That's the 3 cases you really have with the loop, and you want to make sure that you exercise them. Now, depending on the contents of the loop, that might be difficult, or might be expensive. So let's look at this example here. This is the binary search from before. In this case, we have 20 prime paths. Now, 20 is a number we can kind of work with, right? Remember that, no, I'm kidding. So this is one of them. This is the one where you go through and you check both of the conditions and then you immediately exit. So that is the case where the list is empty. You're trying to search an empty range and you've just failed. And you know that is that case because you're going straight from the top and then out. You're not actually even considering any element. So this is the case where you're going from the top, you're looking at the middle element. The middle element is, what is this? This is the one where you update the min, so it's the element is too small, right? And this is the case where you're going back on the top of the loop, right? So you searched it, you didn't find it, you reduce the search space from the top, and then you try again. Okay, so in practice what happens is that the prime path coverage will strike a good balance between the cost of coverage, the quality of the coverage, the number of tests that you need, and capturing loop behavior. So I have a small demo on how it works. So this is the same binary search program, but typed up properly in C. And you build with the new fpath coverage flag that was introduced in GCC 15. What you will be left with is the program, obviously, the BS, and a GCNO file. Here it is again. And then we have a haystack. So in this case, the list that we're, or the haystack we're searching is just constant. That's for the exercise. And it has the element 1, 2, 3, 5. This is the, at least for a bit, the Fibonacci. Might be all the way through, actually. But we have values between 1 and 5,000. And in the main, we just set up the search by taking an argument. It's not a very robust program, but it works for these purposes. If you just run this and get the report from gcov, it will tell you that you have 0 out of 24 paths covered. Okay, we haven't run it yet, so obviously we haven't covered any paths. So we search for 5, which we find at index 3. And you see gcov will report, hey, we have 1 run, and we've covered 12 out of 24 paths. Isn't that great? So there's not an immediate correspondence between the number of tests and the number of paths that you will cover. It's quite likely that you will cover more than 1 path for 1 input. Okay, we search for 6, which we know isn't there. This increases the count to 13 that we've covered. Okay. If we expand this with the branch probabilities flag, you'll see we've actually executed all of the blocks, right? So this has full line coverage at this point with 2 tests. With 2 tests, we've covered every line in here. And for this, the loop header example, or loop header case, we've taken also all 4 branches that we can take there, right? Great, with 2 tests. So if you're subscribing to line coverage, coverage says that you're good, 100%. Green, let's move on. So path coverage works at the function level. It analyzes the whole function, not just individual lines outside of context. But kind of briefly, that means that it actually matters when you're evaluating something where you came from. And as you saw in the regular example, if you came from the path where P is assigned a null pointer before dereferencing, that actually matters a lot. So let's look at the report that's for humans and for some machines, because you can parse this. This is designed to be somewhat parsable. So you would put it in your CI pipeline or something. If you give it the prime path source flag, when you ask for the report, it will actually print you for each path that you haven't covered, by default, the sequence of lines in which order you need to visit them and which branches you need to take, if there are some at that line, in order to achieve coverage for that path. So path 0 is the case where you go through the loop, you start from the top. When you reach a loop header, you need to both not find the needle, and you need the min to be less than the max, and then go into the loop before figuring out that, hey, the needle that we're searching for is actually larger than the middle element, so we need to reduce, or what is it, partition the range from the left. And that's it. That would take it back to the loop, which would be a repeated vertex, right? So it actually shows you need to do these steps in order to achieve the coverage. So this is the case where the needle must be shown larger than the middle element on the first iteration, which is a different case than when you're looking for, or when you're finding or comparing with the needle, and it's larger than the middle element, but on a not first iteration. Those are different. So look for 700, and we get 14 out of 24 paths covered. Okay, good. As I said, this is designed kind of to be So I've been using Unix for a long time, and pretty much any tool that I do will have some idea of scripting support, right? So if you print a prime path source and you grep for the not covered, you will get the list of the paths by number or by the index that you haven't covered. So at least you can get an overview, right? So let's go hardcore at it and just give it every input from 0 to 5,000. And we know that the haystack we're working with has numbers from 1 through 4,000 something. So this should find every element and miss in between every element. And we do that, and we're left with, what is that, 1, 2, 3, 4, 8 paths that aren't covered. Okay. So we've exhausted the search space, so to speak. Our domain is 0 to 4,000 something. And we test every possible input that could possibly make a difference, and we're still left with 8 paths that we haven't covered. So let's look at one of them. Okay, so this is the case where you go from the top, you figure out that this is not the middle element, and then you compare to the, you check, okay, is the smallest element still smaller than the largest element or index that we're searching in? And that's false, okay? So we're not going into the loop. So this is the case where you would skip the loop, right? But this is and then later we're just checking, did we find the element or not? And if not, we want to return the sentinel for not found. Okay, so when does this happen, right? Well, this can really only happen when the range is empty, which also would make the A mid there very undefined, right? Okay, not great. These have to be true at the same time. But also, how can a middle element not be the needle and be the needle at the same time? So this is a contradiction that we put in there. And sometimes you want them, but in this case we definitely don't want them. Right? This does make. So let's look at some report for machines and for some humans, because some humans like this format. I don't know. So in this case, this is a very abbreviated one where it actually prints the exact same information, but it doesn't give you the full line. And it makes sure that every output is on a so you can grab for them. And this is good when you're doing the feedback loop where you're trying an input, measuring, trying an input, measuring, and say, did the path that I'm curious about change without having to parse too much information? So it's a lot more precise. But this shows you both the lines and the decisions that you need to take at those lines. So this is the same path as before, and as just to contrast the two, this is showing the same path that we're unable to cover in a condensed format. And you will notice too that the third column there, with the 4, 6, 7, 8, 9, those are the line numbers, which correspond to the single line output at the top. So the top representation in particular is designed for machines for quick scripting, but it will give you the same information as the larger one for humans. So let's talk about subsumption. So subsumption is one of those words that you can kind of drop out, and usually with C++ people it makes sense because of concepts. But we're going to define it. So to subsume is to include something or someone as a part of a larger group. In coverage, we use the word subsumption a lot. When we say that a coverage criterion C1 subsumes to C2 if satisfying C1 also guarantees satisfying C2. So roughly speaking, that means that it's a stronger criterion. So let's go back to the condition coverage for a second. This is a bit of a deja vu. So the condition coverage question posed is, has every condition taken on both true and false? Well, condition coverage implies decision coverage, because if you exercised every term to true and false, then obviously you have exercised every then and else, right? Condition coverage also implies statement coverage, because if there's a statement in your program, it has to, because of syntax, be reachable somehow, and in order to get there you might need to go through a condition or not. But then if you have full condition coverage, you have to exercise every statement. It follows. Now, prime path coverage is neat because it's a reasonably simple to explain and understand criterion, while at the same time subsuming statement, branch, condition, round trip, MCDC, and definition use. So if you measure prime paths to 100, you can forget about all of these. Or you've achieved all of these, which is great. And especially the definition use, because I cannot repeat the definition of that thing right now. I have no idea. But it is very useful. And then there's a matter of sensitivity. So prime paths are able to detect these dependent conditionals. And it's also sensitive to paths that you cannot exercise, like the one we saw before with the contradiction in it. Oh, sorry. On top of very simple to reason about and providing effective coverage. Now, I would like to take a step back and just iterate that the most important tests that you do are your functional and your requirements test, right? Start there every time. And actually, that's really the only thing that you should be caring about. So, and that means your tests that are derived from properties, they might be hand-rolled, you might have bug reports and stories, you might get them from fuzzing, but these are the important tests, right? Coverage actually just complements or informs testing. If you want to hear more on that, my next talk in this room will be on exactly that. But coverage really is about understanding the tests and verifying what they're doing. And really what that means is about understanding the spec, right? This is information that you feed back into your specification. Now, there is this 90-90 rule. It says that the first 90% of testing accounts or finds about the first 90% of bugs, and the remaining 90% of testing accounts for the other 90% of the bugs. There are some practical limitations with this implementation. There's obviously the path explosion. The only way to really combat that is to simplify your functions. Some heuristics control when the instrumentation pass gives up. We do this in order to avoid ballooning compile times and object sizes, but these are just heuristics. So there is a function for the tree program in Unix, if you're familiar with that. It's a fancy ls. It has 1,429 lines and 31 functions. So I tried compiling it with and without path coverage, but I always enable the coverage, which is the basic infrastructure for recording. And the compile time goes from, 170 milliseconds to right over half a second. And the object size goes up 2.5 times for a 1,400 line function file. That's when I was giving up on one or two of the functions. So if I increased the limit of how many paths that I wanted to instrument and measure, I ended up with a 32 megabyte binary. And when you stripped out the symbols from that, you ended up at 28 for the same file. That's 1,400 lines of C. That gives you a 32 megabyte object file. Not great. So all of this is built on the computer science. Do we have the time to go through that? I think we do. Yes. So this is based on clever path enumeration. I used a paper called the Time and Space Efficient Compositional Method for Prime Path and Test Path Generation. I didn't do the generation thing because test generation is the work of the devil. But their algorithm for just enumerating the prime paths is pretty good in practice. So the way it works is that we compute a component graph. Right? And a component is anything that's properly self-contained that you can replace with this single vertex. And then we find the prime paths in each of the components and the prime paths of the component graph. And we merge each combinations of these, and it saves us from redoing a lot of work. I also, and this is, I would argue, my invention, I combined this with a data structure called a suffix tree. to do a compact, oh, hang on. So I do a compact center representation. So because all of these paths can be ordered, they're strings, so you can sort them. Given the set of prime paths, each path is just assigned an index. And so whenever you do visit a complete prime path, the instrumentation will set 1 bit of information for that. So the size of the measurement is pretty limited. It grows 1 bit per path. So if you have 1 million paths, then it's still reasonably small. In order to do efficient subpath elimination, I use a nice data structure called a suffix tree, which I tweaked a little bit for it in construction. It is one of those that performs really well in practice, but has slightly worse big O notation. If you want to read more about that, it's in the paper. But this is a really good data structure for that. And the use of a suffix tree for these subpaths elimination, when you want to, quote unquote, prime your paths to remove everything that isn't a prime path, I filter them through a suffix tree like you would filtering through a set for uniqueness. And this is just extending the definition of uniqueness to subpaths, which I think was a great idea. And then I do some minor optimization by some folding and removing some redundant code that we otherwise would generate. All right, thank you. Try it out. I think I have time for questions, but if not, then see you next session.